For most of human history, building a civilization meant fighting a defensive war against gravity, extreme weather, and violent physical forces. These environmental pressures drew strict boundaries across the map. They dictated exactly where a city could safely stand and how tall a structure could rise before it collapsed. As our populations scale and our physical footprint expands, we are pushing right up against those ancient boundaries. We are hitting the absolute limits of physical laws. Simply pouring more concrete or forging thicker steel no longer works. Modern scaling hurdles require a level of precision that brute force construction cannot achieve. Modern engineering focuses on the systematic resolution of these physical constraints. It is the process of taking the hostile properties of nature and rewriting them into human blueprints. In 2008, a committee at the National Academy of Engineering outlined 14 grand challenges for the 21st century. These 14 challenges target specific physical limits that affect human health and planetary stability. Some engineers are focusing on unstructured, unpredictable environments, training autonomous robots to navigate spaces built for humans. Others are manipulating extreme temperature gradients, building cryogenic optics that unfold 1,000,000 miles away in deep space. But before humanity can fully conquer the vacuum of space, we have to solve the invisible constraints pressing against us right here on Earth. Building the ecosystems and cities of tomorrow means we must first learn how to engineer the atmosphere itself. At 828 meters tall, the Burj Khalifa in Dubai faces a unique set of physics. At this altitude, gravity is a secondary concern. The primary threat is the wind. This diagram shows vortex shedding. When high-altitude wind hits a flat facade, it forms organized, low-pressure bubbles of swirling air on alternating sides. These pockets create a rhythmic vacuum, pushing and pulling the structure, generating forces strong enough to tear a traditional skyscraper apart. To survive in this airspace, the building's structural shape had to be designed explicitly to fight the wind. Form follows physics. Instead of a standard square footprint, structural engineers designed a Y-shaped buttressed core. This configuration acts as a massive aerodynamic wedge aimed directly into the prevailing currents. As the tower rises, the facade steps back at varying heights. These uneven tiers confuse the wind, shattering those dangerous, organized vortexes into chaotic, harmless turbulence. The Burj Khalifa proves that shapes designed to manipulate aerodynamic forces can disarm natural pressures that would crush a standard structure. While civil engineers deflect the atmosphere to build higher, chemical engineers are mining its composition to directly solve the grand challenge of carbon sequestration. This animation illustrates the primary constraint. They are trying to extract a highly diluted target, carbon dioxide, making up roughly 400 parts per million of the atmosphere. In Iceland, the Climeworks Orca plant acts as a frontline mechanical solution to this atmospheric problem. The plant relies on modular collectors that function like mechanical lungs. They pull ambient air through specialized honeycomb filters designed to maximize surface area contact and trap carbon molecules. But this creates an energy paradox. Running massive industrial vacuums requires electricity, generating more carbon than it removes. The solution is a closed-loop system. The collectors are powered entirely by adjacent geothermal waste heat from the Earth below. This clean energy allows the extracted carbon to be pumped deep into basalt rock formations, turning to stone, safely trapped without new emissions. Climeworks demonstrates that saving our planetary ecosystem requires treating the atmosphere as a manageable chemical system. Both the Orca plant and the Burj Khalifa represent the precise goals outlined by the National Academy of Engineering. Severe natural constraints, whether 100-mile-per-hour winds or 400 part per million ambient carbon, are the exact parameters that force brilliant design. The physical world becomes entirely malleable once you understand and systematically manipulate its rules. Now that we are learning to master the invisible forces of Earth's atmosphere, our ambition must scale to even more hostile environments. We are developing complex hardware capable of operating in the extreme freezing vacuum of deep space. And we are building massive magnetic chambers designed to contain the violent, swirling plasma of an artificial star. By systematically resolving these physical constraints, engineering allows our species to move from merely surviving an environment to thriving far beyond it. We want to build massive, highly capable machines, but before a machine can work, it has to get to the job site. The size and shape of our most ambitious engineering projects are dictated entirely by how we transport them. To peer deep into the origins of the universe, we need an optic larger than any existing rocket. If a mirror cannot fit inside a standard payload fairing, it cannot leave Earth. Back on the ground, heavy industry demands immense mechanical power, yet factories are built for human proportions, with narrow aisles, steep stairs, and chaotic corridors. Traditional heavy machinery simply cannot navigate these spaces. The solution to this paradox of scale is state change. Engineers no longer build static, rigid structures. They design machines built to radically alter their physical form once deployed. Modern engineering is shifting toward kinetic systems capable of continuous physical metamorphosis. This diagram shows the James Webb Space Telescope packed inside an Ariane 5 rocket. To fit a massive observatory into a standard fairing, it had to be compacted into a dense, temporary configuration. Following this path, Webb traveled 1 million miles to the second Lagrange point. This specific orbit locks the observatory into a position where it can continuously block out heat and light from the Sun, Earth, and Moon. Protecting the optics is a kite-shaped sunshield, roughly the area of a tennis court. It is made of 5 ultra-thin layers of Kapton plastic, with the outer layers coated in doped silicon to reflect thermal energy back into space. Deploying this massive shield required extreme precision. The expansion process relied on 295 single point of failure deployments, all executed flawlessly in a freezing vacuum. Behind that shield sits a primary mirror 21.5 feet across. Because a single optic of that size cannot be launched intact, it was divided into 18 individual hexagonal segments mounted on a hinged structure. These segments are forged from beryllium. This metal is incredibly light and structurally strong. It holds its exact shape even near absolute zero. Executing this mechanical origami sequence with zero margin for error was the only viable method for delivering a telescope of this magnitude into deep space. Unfurling the hardware is only the first step. For the observatory to function, those 18 separate pieces must be mechanically aligned to operate as a single, flawless optical surface. Behind the segments, 132 actuators push and pull the mirrors to correct the array's shape. To guide them, the telescope uses wavefront sensing algorithms. This software measures errors in incoming starlight, calculating precise micro-adjustments to achieve perfect focus. Developing the ability to measure mirrors with this level of precision resulted in unexpected terrestrial applications. The same scanning and stitching technology used to map the telescope's optics is now used by eye doctors to create high-definition maps of patients' eyes for LASIK surgery. By achieving nanometer-scale static precision in a cryogenic environment, engineers turned a folded payload of beryllium and gold into a functional tool for looking back in time. Terrestrial environments present a completely different set of physical constraints. Factory floors are defined by gravity, densely packed machinery, and human-scale architecture, which demands rapid, autonomous physical adaptation. Boston Dynamics designed the new Atlas humanoid to meet these demands. They replaced the heavy, restrictive hydraulic systems of previous generations with fully electric actuators, streamlining the machine's profile. This architecture gives the robot 56 degrees of freedom. Fully rotational joints allow limbs to continuously rotate, exceeding human mobility. The chassis is built for endurance, carrying 50-kilogram loads while operating across severe temperatures, from -20 to 40 degrees Celsius. Driving this mechanical frame is a new cognitive architecture. Atlas integrates Google DeepMind foundation models to process complex environmental data in real time. Unlike traditional robots executing rigid, pre-programmed loops, this AI integration allows the machine to evaluate unpredictable variables in its surroundings and autonomously adapt its kinematics to complete the task. True industrial utility is achieved when a machine's physical form reacts to the chaotic physics of the real world, as dynamically as the software running in its processors. The slow, unforgiving deployment of a deep space observatory and the high-speed articulation of an electric humanoid operate on opposite ends of the physical spectrum. These machines show that to conquer the most extreme environments, engineers are moving away from rigid, monolithic designs in favor of metamorphic engineering, synthesizing artificial intelligence with heavy hardware to create a fluid, autonomous robot demands the exact same uncompromising mechanical rigor as unfolding a Kapton sunshield a million miles from Earth. Physical limits dictate the boundaries of design. By prioritizing movement, adaptability, and state change, engineers are continually rewriting what a physical form can achieve. Whether it is adjusting a mirror segment by nanometers or guiding a robotic limb through a factory, success depends on the mechanical rigor to move complex components with absolute precision. This same requirement is currently being tested on a massive scale as engineers attempt to assemble the 1,000-ton sectors of the world's largest nuclear fusion reactor. Every human achievement to date has occurred within a single, highly sensitive biosphere. This environment is bound by a strict thermodynamic ceiling, limiting the total energy we can generate without degrading the system that keeps us alive. Because our current civilization relies on finite, harvested materials, our expansion is physically capped. This energy bottleneck dictates where we can live and what we can build. To move past these physical limits, the National Academy of Engineering established 14 grand challenges, a framework that acts as a master blueprint for 21st century infrastructure. Within this blueprint, two foundational prerequisites are required for long-term survival. We must generate endless energy and establish a permanent foothold off-world. The NAE framework shifts the conversation from theoretical possibility to material execution. Our survival has become a project of pure logistics. In southern France, an international consortium is attempting to solve the terrestrial energy bottleneck by constructing the ITER tokamak, the largest nuclear fusion reactor ever designed. The core physical hurdle of fusion is containment. The reactor must sustain a burning plasma that steadily generates more power than the massive amount of electrical energy required to ignite it. Engineers use D-shaped superconducting magnets aligned to 2 millimeters to hold the reaction. But tritium fuel is incredibly rare. To solve this, ITER uses an internal breeding cycle, using high-energy neutrons thrown off by the plasma to breed new tritium directly within the chamber walls. This closed-loop system allows the massive reactor complex to operate in situ, removing the need for global fuel supply chains. Maintaining that loop requires managing the most extreme temperature gradient in the solar system. The cryogenic magnet supports operate at -269 degrees Celsius, positioned mere inches away from a contained plasma fire hotter than the center of the sun. Mastering this reaction scales energy from a finite extracted resource into an engineered loop. With the energy limit broken, the engineering focus shifts to the second necessity of the blueprint, establishing a permanent foothold at the lunar South Pole through NASA's Artemis Space Camp. Space infrastructure faces a brutal physical constraint. Lifting heavy construction mass out of Earth's gravity well requires a massive penalty in fuel and cost. Launching the concrete and steel required for a city is currently impossible. The logistical workaround is in situ resource utilization, or ISRU. Instead of importing materials, engineers are developing systems to 3D print rigid habitat structures directly out of the local lunar regolith. To operate around the base, Artemis requires two strategic tiers of mobility: an open-top lunar terrain vehicle for short sprints, and a larger pressurized habitable mobility platform for surface expeditions lasting up to 2 months. Powering this mobility poses a specific challenge. The South Pole experiences periods of intense darkness during the 14-day lunar night. To guarantee continuous power, the base will rely on small 10-kilowatt nuclear fission surface units. On the Moon, the environment is the supply chain. Long-term habitation depends on converting hostile conditions into the infrastructure required to survive them. The engineering philosophy used for fusion and lunar habitation applies to any construction pushing against physical extremes. When you build at scale, the laws of physics dictate the shape of the structure. At 828 meters tall, the Burj Khalifa faces violent wind loads. Its tiered, Y-shaped buttressed core was designed to force the wind to break apart, preventing the buildup of vortex shedding that would tear a traditional square skyscraper apart. In a cryovacuum, physical constraints force massive structures to become foldable origami. The James Webb Space Telescope's primary mirror was segmented into hexagons, so the entire observatory could pack into the payload fairing of a rocket. This infographic shows how the telescope manages extreme solar heat. A thermal gradient drops across 5 distinct layers of material, some as thin as 0.001 inches, to protect the delicate instrumentation. To make these separate segmented mirrors function as a single unit, engineers installed 132 individual nano-actuators to align the components with nanometer precision. In these environments, physical limits define the shape of our tools. The aesthetic of a megaproject is the direct result of its aerodynamic and thermodynamic requirements. The final logistical frontier is automation. Human expansion requires systems capable of dynamically adapting to unpredictable physical environments. Robotics design is shifting from rigid hydraulic systems towards highly responsive, fully electric actuators. This hardware is now deeply intertwined with AI foundation models. Rather than following pre-programmed code, robots can autonomously learn new physical tasks in real time, adapting to their environment as they work. The synergy of intelligence and hardware will allow us to execute the macro logistics of the future. Autonomous systems will be the workforce assembling the tight tolerances of the Eider tokamak and 3D printing the Artemis base camp on the lunar surface. The NAE challenges provide the roadmap. By adhering to the absolute laws of physics, engineers are building the infrastructure required to move humanity past the thermodynamic ceiling.